Hello and welcome back to contour integration. We have this particular integral to do today. It's the integral from 0 to infinity of the sine of x over x at x squared plus a squared, where a is a real positive constant. So how do we do something like that? Well, quite clearly we're going to use the residue theorem at some point. So we're going to integrate, we're going to change this integrand some complex function f of z, and we don't really like signs. It's very difficult to parameterize, so we're going to look at the exponential e to the I z over z squared plus a squared dz around some closed curve gamma, which we're going to consider in a second. Well, quite clearly the choice of the contour is determined by the limits. It's 0 to infinity, so really we need to walk along the x-axis. So something like a semicircle would be okay. The problem that we have with the semicircular contour, which is very standard, is this z here at the origin, this simple pole. So we're going to indent it at the origin, the same way when we've done the integral of sine x over x. We're going to use exactly the same contour, and we're going to use similar ideas. Okay, so let's draw what we are going to use. So this is now my complex plane, and my contour is going to be a semicircle of radius r indented at the origin via another circle of radius epsilon. All standard stuff. Once you've done a few of these now, they become fairly repetitive. So that's epsilon to r, and that's from minus r to minus epsilon. What else we need to put? That's our gamma. It'll be traced, of course, as per usual, in an anti-clockwise direction. And unfortunately on the epsilon curve it'll be clockwise there, but overall the gamma will be anti-clockwise. What else we need to put? Let's define these two curves as gamma 1 and gamma 2. So our next step is perhaps to look for the residues of this particular f of z, which lies inside gamma. So that is real z and im z. All right. So let's look where we have poles. We have, of course, a pole at the origin, which we don't really care because outside are gamma. And if we factorize this z squared plus a, we will have, of course, simple poles at z is equal to ai. That's up here somewhere, and somewhere at the bottom here minus ai, but we don't really care. This is going to be outside our gamma, so we just got a simple pole at ai. Let's compute the residue first of all of this particular pole. So the residue of my f, where f of z is all of this thing here, at ai, using the standard formula, is the limit as z tends to ai, z minus ai f of z. So I'm going to write it in factorized form, so e to the I z, and we have the z, of course, at the bottom left, but we're going to write it as z minus ai z plus ai. Of course this will cancel, and when we're putting all of this to, now the limit can be computed, so that's going to be e on the numerator to the ai, and on the denominator we're going to have an ai from substituting into the z, and then we're putting another ai there, so it's going to be a 2 ai, just being careful now with the pluses and minuses because a lot of i's multiplying. So it's going to be e minus a on the numerator, and on denominator we have definitely a minus from the I times I, a squared, I forgot the 2 a squared. I hope it's all good. Okay, so let's say now by the residue theorem quite clearly the integral of this complex function around gamma is going to be, of course, 2 pi I times the sum of the residues of f of z inside gamma, which is only just this one. So 2 pi I times this, so it's going to be times e to the minus a over minus 2 a squared. Okay, so the usual plan for things like that now is to split the gamma into several sections, show that in some of these sections there is no contribution to the final answer, and of course our integral, the real integral that we have up there, will come when we let r go to infinity. So if we blow this picture, so the r goes infinitely large and the epsilon shrinks to 0, then we're going to get our integral from the real axis. Okay, so we're going to go next and say, okay, if we, let's put a curly bracket. So if we integrate, first of all, let's start with the gamma 1, around gamma 1, first of all, plus the integral from minus r to minus epsilon. So we're going this way, then around gamma 2, plus the integral around gamma 2, plus the integral from epsilon to r, close curly bracket, of my f of z dz. The answer, of course, is going to be equal to this thing here, which we can simplify it when we're ready. Okay, so this is just our reference so far. So our plan is, first of all, to check what is happening with this gamma 1 and gamma 2 by suitable parameterizations. In other words, the semicircular arcs. And we're going to start, first of all, with, let's make some room. We're going to start with the outer curve. So I'm going to say the contribution, first of all. I'm going to state it, of course, and I'm going to say something about it. The contribution of, let's put the integral, I'm just writing it in some kind of obvious notation, around gamma 1 as r tends to infinity is 0. By what? By Jordan's lemma. Jordan's lemma is very, very common, is used in semicircular kind of arcs. It's a very good result. It cuts out a lot of the work. What it says essentially, can I state the Jordan's lemma? The proof of Jordan's lemma, by the way, in my book that has loads of this kind of stuff, it has in excess of 30 or maybe 40 questions. I have actually a detailed proof of Jordan's lemma, but within a question you normally state it and use it. What does it say formally, if I can remember? It says things along those lines. If g of z uniformly converges to 0 as the mod z tends to infinity. Let's make some room. And that for argument of z being between 0 and pi. So basically we're considering sort of arcs like this. Then if a is a positive constant, the integral around gamma, I'm going to use capital R, gamma r, and I will define what r is. Gamma r of g of z e to the I a z. That's the general case. In our case, of course, the a is going to be 1, as long as possible, dz. Then if a is bigger than 0, the integral of that tends to 0 as r tends to infinity, where gamma r is, of course, not equal, gamma r. Actually, we can write gamma r is equal to r e to the I theta, again theta between 0 and pi. So if you look at, I hope I've written it sensibly, it makes sense. If g of z uniformly converges to 0 as mod z tends to infinity for argument 0 to pi, then if a is bigger than 0, then this particular integral goes to 0 as r tends to infinity. In a simpler language, because this is a little bit formal, it's probably what you will be writing in analysis classes. It says this: if you have something which is of the form usually like you have it in here, is 1 over essentially that bit here of z cubed. That's how you have to see it, okay? That's the dominant thing at the bottom, multiplied by an exponential. It can have actually a number there, 3, 4, whatever. It has to be positive. Then if you're integrating on the top half of a semicircle of radius r, okay, so that's radius r, and that's your semicircle, then if you, that's your integral around this gamma here, little gamma, okay? If you let r tends to infinity, this has 0 contribution. That's what Jordan's lemma is actually saying. So for this particular case, it does apply, because on gamma 1, we have, of course, e to the iz, which has a positive constant there, and this is of something that will go to 0 as the modulus of z goes to infinity, and therefore the contribution of gamma 1 is 0 in its limiting case. Okay, nothing else to say. Perhaps I even spent too much time actually discussing it today. I don't know if I have discussed this in a previous lecture, but this is quite a standard thing. So we can just say that is it. Gamma 1 has 0 contribution. Okay, what's going to happen now with the rest? We're going to look next at the integral around gamma 2. This is not so easy. Okay, so gamma 2. Gamma 2 is, of course, the little circle, which is there. I'm going to need to parameterize my function, so I'm going to do it here. Gamma 2, on gamma 2, z is a radius of, it's a semicircle of radius epsilon, so I can parameterize it as epsilon e to the I theta, where theta runs, because it's running clockwise, runs from pi to 0 in that particular direction. That's for the limits. And of course we need our dz, so our dz is I epsilon e to the I theta d theta. Okay, let's see now what happens when we're integrating f of z dz around gamma 2. So limits, first of all, let's move out of the way and drag this cable along with me. The limits go from pi to 0, because of course we're running clockwise, we just mentioned that, and we're going to have e to the iz. I, my z, is epsilon e to the I theta. My denominator, I'm going to have a lone z here, so that's going to be epsilon e to the I theta. Inside the bracket I've got is squared, so it's going to be epsilon squared e to the 2I theta plus a squared, and my dz is going to be, I'm going to put this I on the top here, that's the I from there, and epsilon e to the I theta d theta. Loads of stuff that I have to be careful I haven't lost anything, so just checking, last check. So I have substituted in there my z and my dz from this particular substitution. Okay, let's do a couple of things. First of all, let's cancel this epsilon e to the I theta from top and bottom. And another thing that I'm going to do, I'm going to perhaps reverse the limits and make it 0 to pi and generate a minus. So I swapped and generate a minus. I also have an I, a constant there. Let's pull it outside so we don't lose that. And what I've got left now, let me see what I've got left. I've got epsilon, I've got e to the I epsilon e to the I theta, total and utter mess, and at the bottom I've got epsilon e to the 2 I theta plus a squared d theta. And let's think about what happens now to this particular integral. Now, we're going to integrate at some stage, but of course we don't want this particular expression, what is epsilon? We want the limiting case as epsilon goes to 0. So in the limiting case, as epsilon goes to 0, so basically you can think of it as interchanging limit and integral there. We can actually see that the denominator, the dominant term, of course, is the a squared. As epsilon goes to 0, this thing here will vanish. So on the denominator, we're going to have, let's leave the minus I there, and the 0 to pi. On the denominator, we're going to have just an a squared left over. And on the top, as epsilon goes to 0, we're going to have e to the 0, which is 1, d theta. So this particular integral will produce, this is of course another constant, we can pull it outside, so it's minus I over a squared, and the integral of d theta, 1 d theta from 0 to pi is another pi. So this is now the integration around gamma 2 for our f of z. So before we lose this particular thing, let me write it in red pen somewhere. Because with my luck I'll probably rub it off and then I won't remember it. This is this bit here. Let's write underneath that. So that is going to be minus I pi over a squared. So that's around gamma 2. All right. So now we have practically all our bits and pieces, because of course we have let r tend to infinity. The effect of that will be 0 contribution around gamma 1. So we have blown the outer curve forever, and we have shrunk the epsilon to 0. So that produces some contribution. So we can finally say now that as r tends to infinity and epsilon goes to 0, this particular line, of course that doesn't cancel, but we're going to have the integral from minus infinity to 0 of my f of z. Let's write it in that form first of all, dz. I'm going to write this one next, plus the integral from 0 to infinity of my f of z dz. This particular contribution, careful because it's negative, plus the integral around gamma 2, which I have evaluated, so it's not a plus, it should be a minus in there, minus I pi over a squared. Of course, it should give me 2 pi I times this thing here. So can I tidy this up a little bit perhaps? The only thing I can lose is just the 2's really. So it's equal to pi I e to the minus a, and on the bottom I've lost the 2 because I cancelled it of course here and here, but I've got a minus minus a squared. At least we got a common denominator. So all we're left now is we of course along the x-axis the z is equal to x, so we're going to get now e to the ix over x squared plus a squared dx. Let me write it, it doesn't really matter, I'll put the limits in a second. E to the ix x squared plus a squared dx, and that's of course from minus infinity. On the next line I'm going to put them together, and that is 0 to infinity. It's going to be, I'm going to tidy this up, so it's going to give me an I pi positive over a squared minus another I pi over a squared e to the minus a. So hopefully it's all good. Let's clear the board a little bit. So we've got a bit of space. We're practically at the end now. We're going to get integral from minus infinity to infinity of e to the ix over x squared plus a squared dx is equal to, let's factorize the I pi over a squared, and that will leave us 1 minus e to the minus a, and split the integrand into real and imaginary. We have it from 0 to infinity, so of course we're going to get an odd and an even part. So if we write it minus infinity to infinity, that's of course the cos of x. I'm going to write it in 2 bits straight away, x squared plus a squared plus I sine x from the exponential x squared plus a squared dx. is equal to, and of course you can argue either way that one of these integrals, of course, 0, either by comparing real and imaginary or by looking at odd and even parts. For example, clearly that's all real. This is all imaginary or complex if you want, and therefore this will be 0. But you can also say the cos is even, this is odd, this is even, odd times even is odd, and then even divided by odd is of course odd. So that has there's nothing there. And if we conclude basically that I'm gonna pull the I outside the integral, minus infinity to infinity sine x squared plus a squared dx is equal to I pi over a squared 1 minus this, and of course the i's we can now throw away, and this is an even integrand, so we can actually say 2 lots of my integral sine x squared plus a squared dx is going to be that. And I'm sorry, I will not be able to fit the very last line, so I'm gonna cheat a little bit here and say, okay, we can now divide by 2, and I'm going to get this particular answer. And I hope it's the correct answer, because I didn't check again. I keep doing the same thing for the answer for this particular one from my book. But it looks kind of like the thing you expect to get for something like this. I hope you followed it. I'm not quite sure which lecture is that, but I will do quite a lot of different types of integrations just to give you a bit of working knowledge with this kind of stuff. And I hope you find it useful, most importantly. And who's laughing now?